So welcome everybody to the webinar of today. The speaker of today is Cattafesta, and he's gonna talk about adaptive separation control of a laminar boundary layer using online dynamic mode decomposition. So as usual, I introduce the speaker very briefly, and then I leave him the floor. So since August 1st, 2022, Luis Cattafesta III is the John and G and Jane E. Olin end-to-end department chair in mechanical, material and aerospace engineering in the Armour College of Engineering at the Illinois Institute of Technology. Previously, he was at University of Eminent Scholar and/or professor in the Department of Mechanical Engineering in the FAMU FSU College of Engineering. He received a bachelor degree in mechanical engineering in 1986 from Penn State University and a Master of Science degree in aeronautics from MIT in 1988 via AF-RAPT fellowship and a PhD degree in mechanical engineering in 1992 from Penn State University. In the same year, he joined High Technology Corporation as a research scientist at NASA. His research at NASA largely focused on supersonic laminar flow control and pressure and temperature sensitive paint measurement techniques. And in 1996, he was awarded the 1996 NASA Team Excellence Award for his contributions. At that time, he became involved in active control of flow-induced cavity oscillations, which provoked his current research interest in active flow control in aeroacoustics. He joined the University of Florida as an assistant professor in 1999 and was promoted to an associate and full professor, respectively, in 2003 and 2008, before joining Florida State University in 2012. Funding for his research has been provided by grants from NASA, AFOS, ONR, NSF, Boeing, Lockheed Martin, General Electric, Gulfstream, among others. Dr. Cattafesta has co-authored for AIAA Best Conference Paper Awards in 2001, 2002, and twin 2004. He is the author of and co-author of 7 US patents, 7 book chapters, and more than 100 archival journal publications. Dr. Cattafesta is a fellow of IAAA, ASME, and APS, and the Royal Aeronautical Society. He's also a member of ASA, and he's currently associate editor of Experiments in Fluids. So it's with great pleasure that I leave the floor to Luis Cattafesta. So Lou, I stop sharing my screen and you can start sharing yours.
All righty. Thank you very much, Francesco. So can you confirm you can see the screen?
Yeah.
Okay, excellent. So thank you very much for the opportunity to give the seminar today. As you know, I spent the summer, largely the summer, I think it was 2019, prior to COVID there in Lille, and was working largely at ONORA, one of your partner institutions, and got a chance to meet several of you. So this is a nice opportunity to at least reconnect virtually. So today I'm going to talk to you about a project that we completed not too long ago. Was essentially the PhD work of Eric Dean, who's now working in high-speed, actually hypersonics at Lockheed Martin. And so this was work that was funded by the Air Force with our program manager, Greg Abate, and I'd like to acknowledge that support. And also the collaborations that I've had over the years with Rajat Mittal and Clancy Rowley, who were involved in this research, as well as Maziar Amati at the University of Minnesota. So today I'm going to focus on the experimental aspects of the flow control problem associated with control of a separated laminar boundary layer. First, let me just say a word or two about Illinois Institute of Technology. So you can see this in the background, the skyline of the beautiful city of Chicago. And IIT is located just on the south side of the city. And I'm pointing here to the location of our building in Retaliata building, adjacent to the L that goes into the downtown and the expressway on your left-hand side. We have a joint program between mechanical materials and aerospace engineering. And if you're interested, I'll leave you here the website. And presumably there are some students that you have in your undergraduate and perhaps in your graduate program there that might be interested in some opportunities to study abroad. And I leave here an email for Ms. Benita Mesquita, who's in charge of our opportunities for international students. And feel free to reach out to her, to me, for more information about those opportunities. So moving forward, I'm going to talk today about controlling this very separated flow. And this is actually a time-resolved PIV image of the separation. And I'll talk a lot more about this as we proceed, but I wanted to start off with this picture so you get an idea of what we're talking about. So we have an incoming boundary layer that's moving from the left to the right, and you can see a separation. I'll explain how this actually occurs, where we induce a separation bubble. So you can see how the shear layer actually lifts up off of, let me do a laser pointer here. So you can see how the incoming boundary layer lifts up, and you see this roll up through a Kelvin-Helmholtz type instability. And then you get this closed separation bubble. So it reattaches somewhere downstream here. So it's quite obvious from all of your backgrounds that you're quite familiar with separated flows and all the applications that it occurs in, and the implications that it has in terms of loss of lift on steady loads, and whether it's in airfoils or compressors and turbo machines, diffusers and the like. So a little bit of background on this. So if we look at this in the context of, say, some foil, and we have this approach flow, essentially you can look at three characteristic frequencies, those associated with the wake, those associated with the shear layer that you saw on the previous page, and when the separation bubble itself closes, you can have oscillations in the separation bubble. So typically, these frequencies are non-dimensionalized into a Struhl number. In the literature, this is often called F+. So it's F times some length scale associated with this. For example, the length, the size or length of a separation bubble normalized by the approach velocity. And we're interested in controlling this thing through an interaction. See if I can get this to advance to the next page. So if you look at the literature of some prior work on this, it's been pretty well established by a number of researchers that forcing at an F+, this non-dimensional frequency corresponding to this characteristic frequency of the shear layer, that is of the roll-up of those vortices, appears to be the optimal in terms of the ability to control this, at least in an open loop sense. Now, it's interesting, there was some other work where Raju et al. Looked at what happens when you change the location of the actuator relative to the separation bubble. So it's obviously most beneficial when it's just upstream of separation. So the example that they show here is if you move the actuator location right up to the leading edge, they find that the optimal forcing frequency is not the shear layer, it's actually that of the wake, so the much lower frequency. And if they move this just a little bit aft downstream, then the optimal frequency is that of the separation bubble itself. So it stands to reason that there's no one single frequency that is optimal. One of my former students, Yi-Tian, studied adaptive control, and this illustrates some of the complications of this. So you're looking at an airfoil, a NACA, rather thick NACA airfoil, and PIV images of smoke flow visualization and a pretty high angle of attack. So you can see that the flow separates off of the leading edge of this, and you have this large stall cell that appears. And this is at a chord Reynolds number about 120,000. So he studied using arrays of synthetic jet actuators and arrays of pressure transducers, methods to control this using adaptive control algorithms, and found that when we use the pressure transducers to sense the state of the flow, there were some problems with doing this. It was effective, but because these actuators make a fair amount of noise, and anybody who's worked with synthetic jets knows precisely what I'm talking about, the sensors don't know whether the signal that they're getting is acoustic or hydrodynamic. So essentially a characteristic of the control would be that it would establish control, but then in an effort to continue to suppress the oscillations that it was detecting in the pressure signals, it would figure out that what it needed to do was turn the actuator off, and then the flow would separate again, and this whole process would repeat itself. So we were looking for something that was a little bit more advanced than this, that was maybe more physics-based. Now, it's fair to say that active flow control has primarily been done in a largely open loop, perhaps you might even say ad hoc fashion, through a really expensive trial and error process. Now, there's all the rage in machine learning techniques today for adaptive control. And there's examples of this even years ago. So for example, Yi that I just mentioned, ETN, looked at a downhill simplex method where there's no model. All it was trying to do was to maximize the lift to drag ratio. And it did this through a measurement of a load cell of the lift and drag. And it was able to do this successfully as illustrated in this top row, but it did it at a time scale of about 1 Hertz. Another student in the lab, Mr. Reese or Dr. Reese, did this using a radial basis function neural net. And again, this was extremely successful at doing this, but this was even an order of magnitude slower. So this took about 30 seconds of actual physical time to develop a model that was suitable for control of the lift in this particular case. So we want to be able to do this on a time scale that's much faster. So the benefit of these is that they're model free, but of course there's a lot of people that have focused on more physics-based approaches. So for example, one of those is using the famous Galerkin projection, where you use proper orthogonal decomposition of the spatial modes to do this. The problem with this approach is that as you control the flow, the baseline flow changes. That is, the basic state changes, and the model that you develop is no longer valid, particularly if you're going from a largely separated flow to an attached flow. So your model needs to adapt in order to be able to do this. And we would like to do this on a time scale that is on the order of the fluid dynamic time scales, instead of these long time scales that I indicated above. So a little bit about the experiment. As I showed you on the first movie slide, this is occurring on a flat plate. So the flat plate itself spans the width of the test section, and you can see its chord is about 40 centimeters long and it has an elliptical leading edge. And for the cases that I'll show you here, we've got a chord Reynolds number of nominally 100,000. And you'll see that where the separation occurs is just going to be downstream of this location. And we have a slit that roughly spans the central 2/3 of the model. It's a zero net mass flux actuator. And this is what is forcing the flow. And then for flow sensing, we're using an array of inexpensive, these are electric mics, 13 of these. And these detect the instantaneous state of the flow, and they're closely spaced about 2% of the chord between them. So how do we get this separation bubble? The way it's done is by using a fan on top of the tunnel that pulls some fluid out of the upper boundary and re-ingests it just downstream into lower. So it's a zero net mass flux boundary condition that was motivated by some work published by Ney and Moyne and JFM in the late 90s. So it produces a very canonical separated flow that enables you to study this in a framework that enables computations. So for example, my colleague Rajat Mittal at Johns Hopkins does large eddy simulations, and he could use essentially rectilinear grids that are highly clustered near the wall with great ease and go to reasonably high Reynolds numbers that match what we have in the experiments, at least for large eddy simulations. So that was one of the motivations for doing this. All right, so just showing you here the PIV. I'm going to show you two different regions that we use for PIV. One captures the entire separation bubble, and the second smaller region that I show you in the middle is measurement right around the location of the actuator. So using this, we can actually compute the momentum flux, if you will, that's coming out of the actuator, so a much smaller scale. This is a movie showing you, or at least a snapshot of a movie showing you the lift up of the separation and formation of this shear layer, and then this mean reverse flow region. And what we'll see here is that if we use the length of this separation bubble as the characteristic length scale, it's about 24% of the chord, and alternatively the height of the separation bubble, which is around 1.7% of the chord, we can characterize this Struhel number based on that and the free stream speed. And remember, this is around 2. So this is the characteristic frequency of this. So I mentioned to you the zero net mass flux actuators. So we have an array of piezoelectric discs or piezoceramic discs. There's 4 of them inside of the cavity that spans the central 61% of the model. And these oscillate in phase, and they produce or synthesize a jet. So you're actually seeing a picture of the PIV that is used to measure the flux that's coming out of here. So the slot itself is about 2 millimeters. And in order to excite the low frequency information that's relevant in the dynamics, we actually use a modulation approach that's called burst modulation. So you're probably familiar with amplitude modulation. Burst modulation is quite similar to it. It's essentially multiplying the sinusoidal waveform by a square wave. And so this is an illustration of that, where this high frequency oscillation is about 2 kilohertz, which is essentially the actuator resonance frequency. And we're multiplying it through by a square wave that has a duty cycle, meaning when it's on and off, by about 50%. And this actually occurs at a much lower frequency. We call it this modulation frequency, which is tantamount to the characteristic frequencies of the flow. And that's how we obtain control authority. So you'll hear some terms that I'll use here. I've already mentioned some of these. So the momentum that is injected into the flow is normalized into what's called a momentum coefficient. And it's essentially characterized by the jet area and the RMS, or the mean squared velocity of the jet. And then the forcing frequency, remember I used an F plus, will be this modulation frequency, this low frequency modulation, at least in an open loop sense, into a Struhel number, which we call F plus. So one of the first things that Eric did was see how receptive this separated flow was to the synthetic jet. And what you're seeing here is the height, the normalized height of the separation bubble versus that forcing frequency at 2 different values of C mu. And so the baseline separation bubble height with the uncontrolled flow is this dashed line. And you can see that we're able to achieve, using open loop control, a pretty broad range of forcing frequencies will reduce the height of that separation bubble. So there's no clear one frequency that jumps out at you as the best. And you can also notice that if you increase the momentum, as you might expect, you get a further reduction in the separation bubble height. Okay, this is an instantaneous snapshot of the baseline separated flow. And this is a snapshot of the case where we're forcing at this F plus around 1.9 with the corresponding C mu. And you can see that what's happening here, it's clearly reattaching this flow and creating a turbulent boundary layer further downstream. And then this is just one other case at a slightly different condition. The mean separations corresponding to here, indicated by the black line superimposed on vorticity, shows you here that you have this separation bubble, and it's almost eliminated, not completely, in these 2 different cases that I illustrated, instantaneous snapshots just a little bit ago. So it's quite clear from this that the separated flow is receptive to the forcing. The question is, how do we, if we want to do this in closed loop control now, are there any advantages, and what kind of modeling approach might we use? So we explored 3 different approaches, and we wanted, remember what I said at the beginning, is we wanted something that enabled us to produce an adaptive model that would retain the essential physics. And we wanted this to be relatively fast. So when I say relatively fast, I mean we want to be able to do this on the timescales of the fluid dynamic structures. And remember, we also want this model to be adaptive, because as you control the flow, the baseline state is going to change. And so the model is likely going to have to change. So Eric looked at Galerkin projection. He looked at a dynamic mode decomposition, which uses the POD temporal coefficients. Both of these used 20 modes. And what I'll really focus on today is the online DMD, which I'll tell you about. And in this particular case, we're actually going to use the surface pressure microphone measurements. So the array of 13 microphones. This is going to give us our significant reduction in dimension. And the question is whether that will enable us to do this in real time. So a little bit about dynamic mode decomposition. It's quite popular now. Thousands of papers being published on variants of this in a variety of applications. Simply stated, if you take your data, whatever it happens to be, and you form 2 matrices, so each column, X1, X2, X3, etc., all the way up to the nth column, is a snapshot in time. So you form this data matrix, we'll call it X, and you notice that Y is 1 step ahead, okay? So it's shifting in forward in time, just 1 time step. So this matrix A that does this mapping, okay, in a state space framework, if you think about it, is what's called the transition matrix. And you can find the transition matrix using the pseudo inverse. And the benefit of this is that it provides essentially a linear representation of this nonlinear system dynamics. And in some sense, it is an approximation of the Koopman operator, which is an infinite dimensional operator of a nonlinear system. How do we interpret this? Each POD mode oscillates at a particular frequency. So if you take the snapshots, whatever the data happens to be, and perform the DMD on this, and analyze this DMD matrix, essentially the eigenvectors of this are the modes, and the corresponding frequencies of this, the eigenvalues, come from that. We can also look at the characteristics, the amplitude or energy of these modes averaged over time. In our case, we do it spatially and temporally, so we get an RMS spatial average of these modes and look at these as a function of frequency. And when Eric does this, I just want to show you some of the frustrations that come up. So if he uses the POD coefficients as the identified predictions, if you will, of this model, a 20th order model, and he marches forward in time, and we look at the first, second, and third mode of this versus time, you can see that initially it stays pretty close to the actual POD coefficients that come away from the time resolved PIV. But eventually they diverge, okay? And so this is well known to be a problem when you use these sort of projection-based approaches. So it was clear that we needed something that is constantly being fed new data and learning kind of on the fly. So that drove us to this online DMD approach. And so this is physics inspired, as I just illustrated, but it's data driven. And what it will give us, as you will see, is a linear discrete model that will be adaptive on the fly. The states that we're going to use are actually going to end up being the 13 pressure transducer data points that come out of this measurement of the array, okay? So the idea is that we're going to take, if you think of a phase space plot, and you have some sort of oscillator model evolving in time, okay, you get this behavior where when you induce forcing, you want to drive the states to 0, okay? So a smaller radius, if you will, of this phase space. And so that means the model's changing, and we need to be able to update the model in order to incorporate this. And you will see that we do this by using a very simple linear quadratic regulator that is based on a measurement of the states. The states are that of the pressure transducers that are detecting what's going on the surface. And you'll see that when we do this, this is an optimal control framework, and we need to define what states and what the penalty is that we want to use. And I'll talk about that shortly. Okay, so if we take the PIV data that I showed you, there's essentially the number of measurements times 2 components for 2-component PIV. So you have a dimension, if you will, that's like 20,000. And this is just to illustrate this. If you take 10,000 snapshots, and then we perform what's called total least squares DMD, which reduces the bias in the DMD analysis, and you plot the eigenvalues, and I'm showing you a portion of the unit circle, all of these fall right on the unit circle, which is what you would expect. This is essentially the limit. It's not, they're neither growing nor decaying, so they should fall right on the unit circle. And if we look at the most energetic mode, which is right at a Stroll number about 2 that I mentioned earlier, and then plot what that mode looks like, this is the real part of that mode at this corresponding frequency. And you can see essentially or visualize the structure of that shear layer that was lifting up off the surface and rolling up into these discrete vortices. And so the idea is that clearly these things are going to be propagating along the plate, and they should leave a footprint that can be detected by the pressure transducer array beneath it, right? I don't know if this movie will play or not. Let me see. Doesn't want to play. But essentially, if this movie were playing, what would happen is this thing would just be evolving. You would see these structures just propagating downstream. Now, clearly, we can't use the PIV for real-time control. It's not practical. It enables us to see the flow physics and maybe link what we see to what we can actually measure and implement real-time control using the time-resolved surface pressure measurements from those microphones. So what we first wanted to do before we jumped right into it is actually try and compute pressure from the PIV. And we used a well-established method of pressure-based PIV with all the caveats associated with the fact that we're taking a slice of what is essentially a 3-dimensional flow, and we're essentially zeroing out all the 3D terms that we don't measure. And we solve the pressure Poisson equation. Okay, so essentially you have the Laplacian of the pressure, and on the right-hand side, you essentially have the Q, okay, which comes from the PIV snapshot measurements of the flow. We implement the boundary conditions in the domain, in this limited domain, based on a approach adopted by Descartes and documented in experiments in fluids. And I'm going to show you the result of this on the following slide. So the top is showing you after initial transient, we're computing the vorticity, and I'm superimposing quiver plots on top of this. And beneath it is the pressure fluctuation, okay, the unsteady pressure fluctuations. And you can see that these structures are clearly associated with the peaks and valleys of these vortices, and they're propagating along the length of the plate. And so you see a correspondence between these two. If we superimpose snapshots of this at different time delays of the pressure contours on top of the vorticity, you can see a clear convection of these disturbances as you go to higher and higher time delays. And these are consistent with cross-correlation measurements that we make on the surface. But we think we've got the physics right. And that means that really, if there is a mapping or a footprint of the pressure on the surface from these vortices that are propagating, we should be able to detect them and then use that as a basis for control. So now I want to do this real time. So this is a trick that Clancy Rowley's student, Dr. Zhang, came up with. It's a pretty clever trick. So remember that I told you that the state matrix Okay, this transition matrix of A matrix, which we don't really want to compute, we just want to know its spectral properties for most applications. But in flow control, we actually need to know this matrix in order to implement control. And so we're going to say that it's a product, remember, of the matrices Y and the pseudo inverse. So if I look at this pseudo inverse relationship, you can see that I'm going to break this apart into two different products of matrices. So the first one, Y times X transpose, I'm going to call Q. And the second one is the inverse of X times its transpose, and we'll call that P. Okay, so the idea is, remember, you're taking a new set of data, and this then increments X and Y. So we'll call that X at K plus 1 and Y at K plus 1. So what we do now is create these augmented Q and P matrices. So we had Y, and now we add its new value. We had X, and we add its new value. We multiply this out, and you can see the updated Q is straightforward. It's just a matrix multiplication. On the other hand, when you calculate the P matrix, because of the inverse, okay, this is what slows you down if you want to do this at very, very high data rates. So to circumvent this, we use the Sherman-Morrison formula, which essentially does this in a recursive fashion. So you see that the inverse is related now to a series of just matrix, very simple matrix multiplications. And this is a scalar, gamma, which is easily computed on the fly. Once you have this, now you just use this to compute this updated DMD matrix. So you're doing this literally on the fly as you take in new data. And I'll tell you how fast it goes in a second. Now, this is clearly just when you have autonomous systems. There's no forcing. So how do we do that? Well, basically, we extend this using an approach by Proctor, where we create these augmented matrices. So when we do control in a state space framework, we now have some matrix B and the input U. Okay, so all we do is we take the ADMD matrix and augment it with this B matrix, and we take the X matrix and augment it with our control. And then we do exactly the same procedure that I showed you in the previous slide. So this now allows us to do online DMD on the fly, implementing control. Okay, and so one last point that I want to emphasize here is that we're introducing a weighting factor here. And this weighting factor essentially allows us to either aggressively attenuate old data, so it only remembers the new data, or you can let it remember, essentially it's a history effect, by letting this kappa go closer and closer to 1. Turns out that it's very insensitive to this through experimentation, but nonetheless, this is a parameter of this. And I'll talk about the value that we chose in a second. So how does it work? We take the surface pressure microphone array that I showed you. Remember, there are 13 microphones. So this allows you to compute a series of complex conjugate modes associated with them. And this is how it works. So I'm showing you time non-dimensionalized by the shear layer frequencies. So you think of this as the number of cycles of that oscillation. So after a random initialization, so you start off with random numbers, and after about 15 cycles of oscillations of that shear layer, it settles in. And you can see that it settles in on this several frequencies. The one that is most pertinent here is this. Remember, the shear layer frequency was around 2. And this is what the real and imaginary part of this looks like from those 13 microphone array element. And so this actually ends up showing you a propagation at this particular frequency of the footprint of the vortices moving over it. So now we've got this model. We're able to do this online, meaning running it real time, and we want to now control this. So we're going to use negative feedback using this linear quadratic regulator approach. And I'll talk about how we adjust the weighting of this, the penalty term associated with the actuator. I'll then talk about how fast this works, how quickly we can establish control. And finally, I'll show you some results where we say, okay, what happens if we actually change the flow condition? What if we change the Reynolds number, increase it or decrease it? How does it work there, and how fast or slow does it work? So let's first talk about LQR. So this is a standard linear optimal control approach. So essentially, just to refresh your memory, or if you're not familiar with this, it's pretty simple. So imagine you have some states, and with a linear quadratic regulator, we're measuring the states in this case. We're actually measuring, the states are what's measured by the microphone array. So using negative feedback, this is our control. Well, fine, what is the control? It's actually some amplitude. Remember, I talked to you about a burst modulation that was a square wave signal. And we're running the actuators at their carrier, their high frequency resonance signal. We just want to change the modulation amplitude. So if we can compute this K matrix, we have our control. So when you make the assumption that it's this negative feedback, then it changes your state space model into A minus BK. So essentially you could think of this as moving around the poles of your system. How do you get this K matrix? Well, it comes from minimizing a cost function over all time. And the cost function has two terms. So first term is, if you look at it, it's essentially X transpose X. So that is the power of the measured states with a weighting matrix Q. And then there is a second term, and this is, if you look at it, U transpose U is essentially your actuator input, again, weighted with this matrix R. Depending on the magnitude of R, okay, you can really penalize the actuator. Remember, it costs you money to run this thing, or you can not penalize it at all and let the actuator work as hard as you want. So there's some play in this. So essentially, what happens is you get K by minimizing this cost function. And it turns out, if you look at this, we have the A matrix, the B matrix. This is all coming from our control input. What is unknown here is this P sub R. It comes from solution of the discrete time algebraic Riccati equation shown here. So we actually end up running the real-time control. And what we do is we identify the A matrix on the fly using DMD. And then we solve the Riccati equation on the fly as fast as we can to update the K matrix and hence the control. How fast does this work? The primary loop rate is roughly 2 orders of magnitude higher than the shear layer frequency. The shear layer frequency is around 100 hertz. And so this means we're running this on a DSP chip in a PXI, National Instruments PXI system, and it's running at about 10 kilohertz. So we're bringing in 13 channels. The LQR gains are done at approximately 250 hertz, which is about 3 times the shear layer frequency. So we're still satisfying the Nyquist criterion. The Q matrix is essentially just the identity matrix with a scalar factor. And I'm going to show you what happens when we change the weighting, the penalty term on the actuator. I also mentioned to you this kappa term, which is how quickly you forget past snapshots. We set this at a value that you get about 10% attenuation in the snapshot after about 35 cycles. And as I said to you, it's pretty insensitive to this based on experiments. So here's a baseline measurement where there's no control, and you can see the mean separation bubble shown here where we have vorticity plotted. And then when you institute the control, we get a reduction, a significant reduction, not a total elimination of the separation bubble height. And the C mu that we measure using that embedded PIV system, only to measure the velocity in the vicinity of the actuator, tells us what C mu is. Okay, so you can see you get a significant reduction. Well, it turns out, like I said, you can vary R, the weighting term or the penalty term for the actuation, over a wide range. And essentially what this means is you get a Pareto form where you're trading off the performance, and the performance for us is the height of the separation bubble normalized by the chord versus C mu. And so all the closed loop control cases are essentially falling along this front, okay? So you can imagine as C mu gets larger, if we went higher still, we could have closed off the separation bubble completely. On the other hand, if C mu goes to 0, we ultimately achieve the baseline case over here. All the other open loop cases, which are run at a variety of frequencies and levels, do at best what you can do with the closed loop control. All right. So that in itself, I think, is quite interesting. Let's look at some specific examples of these results. So again, here's the height of the separation bubble. And now I'm plotting it versus this penalty term. And the lower plot is C mu. So you can see as I penalize the actuator by going to larger and larger values of R, you see C mu drops. When C mu drops, we get a larger separation bubble. On the other hand, as I back off on R, you can see that C mu will increase and the size of the bubble will decrease. So let's look at two specific cases. If R is set to 2, we get a corresponding height of the bubble and a C mu. If you compare this to the best open loop case that we have for this particular case, we get a 30% reduction in the C mu for the same separation bubble height. Alternatively, if we choose R equal to 1, we get again a separation bubble height and a certain value of C mu. This turns out to give you a slightly smaller separation bubble, so better results than the best open loop forcing case that we have. All right. So what does the signal actually look like? What does the control signal do? It's not sinusoidal. So it's actually quite interesting. So I'm showing you plots, essentially spectrograms, where frequency is on one axis and time that's normalized, again, number of shear layer cycles along this axis for different values of penalty. So remember, as R gets bigger, you're penalizing the actuator more and more. So what you see is when you start off at tau equal to 0, you have essentially very low values of Struhl numbers. And then after about 10 shear layer cycles, it tends to settle in at a forcing frequency that's not 2, which was the baseline's dominant mode, but slightly lower than that, at about 1.5, as you can see in all these cases. And what's interesting is after about 300 cycles, the actuator, you'll see it establishes control, and what it does is essentially just do broadband forcing. Okay, so it's no longer forcing at any particular one frequency. The exact mechanism of what it's doing is unclear at this point. How fast does this work? So here what we did is Eric was measuring with time resolved PIV. He turned on the control and he was measuring this with the time resolved PIV, and he was computing essentially a running average of the separation bubble and then extracting from that its height. And you can see that go from the baseline at the initiation of control, and after about 10 cycles, okay, that's about 1/10 of a second in physical time, you establish control, and then he can hold it for quite a long period of time. I wish I could play this movie for you, but essentially it shows you the initial time over this, and it doesn't want to play for some reason, but essentially what happens is you can see the shear layer just attach and create a turbulent flow thereafter. So finally, in the interest of time, I'll just show you how robust is this control to varying the Reynolds number and how fast is it. So you can imagine, remember the baseline Reynolds number that I showed you was around 100,000. So if we lower the tunnel speed, we get lower chord Reynolds numbers and the shear layer frequency will go down. On the other hand, if we increase the tunnel speed, okay, in this case to 1.25, the shear layer frequency will go up. And we get corresponding changes in the baseline uncontrolled case. So lower Reynolds number leads to larger separation bubbles in the baseline case. And then when we turn on the control, again, we just turn it on, 0 initial conditions, all random values, and it establishes control. And indeed, in the higher Reynolds number case, it completely attaches the flow. And so the behavior, it's quite robust. You control, we don't have to sit there and tune this and run experiments for any extensive period of time. There's no knobs to adjust, just does this on the fly. And the performance is basically the same in terms of its transient response. So I'm showing you here, how does the height of the separation bubble vary versus time? And again, you can see after about 10 to 20 shear layer cycles, which is about physical time, 1/10 of a second to 2/10 of a second, boom, this flow is attached and it stays attached. And what's nice is the actuator power, when it's attached, actually reduces. So the cost of running the control is also reduced. So unlike open loop control, where you're sitting there running this thing perhaps close to the maximum authority of the actuator, here you're establishing control very quickly, it adjusts, and then it stays. So let me wrap up by just summarizing this and showing you that I think that we've developed a method here, at least for a laminar boundary layer, admittedly the easiest case, to create an adaptive separation control approach. It's economic. It uses those electric mics, which are very inexpensive. And clearly it's enabled a path that eliminates a lot of the trial and error that's associated with these extensive parametric studies. The negative feedback control reduces the separation extent autonomously. We did this using LQR. I showed you variations in Reynolds number and the transient response. Now, obviously, there's some things that we can do better, and there's ways that we could extend this. So, for example, one of the things that we're interested in doing is, well, what happens if we go to a turbulent flow? Now, the dynamics are presumably going to be more complicated. How well will it work in that case? That's something that I have a student working on now, and hopefully be able to report on that in the not too distant future. The other thing that comes up is we use a simple LQR approach, which is just a linear framework. What if we actually analyzed the results and came up with a finite horizon based control or some other type of control approach that perhaps has better performance? That's an interesting question, which is really beyond my capabilities in terms of linear control. But I still think it's an interesting question to look at. And you've got the framework here to look at other machine learning based approaches in addition to this physics inspired approach. So with that, I'll stop here, and I'm happy to entertain any questions that you may have. And thank you again for the opportunity to chat with you.
So thank you very much, Lou, for the very interesting talk. So as you just said, let's see if there is someone who would like to ask a question just to the participant. Just feel free to unmute your mic and ask the question, or you can write in the chat. I can report it. Okay, so I don't see any question in the chat. I can start then with one question myself. That's related to what you explained actually at the end, when you compared how the control is actually changing after having suppressed initially the separation bubble, right? Mm-hmm. So is this the same kind of physics of what you explained at the beginning, where you said the frequency is going to change if we control the wake rather than controlling a separating bubble? So whenever the bubble is small, then the nonlinear effects of the bubble are quite less dominant, and so we can kind of tame them down, or?
Yeah, I think that's so that's very, very much the point, is that, remember I showed you with actuator location relative to the separation bubble, the so-called optimal frequency changes, the length scale is changing, so the size of the bubble is changing, so the optimal frequency changes. Mm-hmm. And this approach doesn't predispose you to determining what the shear layer frequency is or what the bubble frequency is. It just says that there's oscillations. These are non-desirable. They should manifest themselves on the surface of the plate. And the array of transducers enables you to identify these modes, if you will, and then try and suppress them no matter what frequency they occur. Mm-hmm. Ultimately, when it attaches the flow, which is quite evident, the question comes up, well, what is it doing now? And it looks like what it's doing, and this is just a hypothesis on my part, is that it appears to essentially trying to create a trip to make the flow turbulent. It's figured out that the easiest way to do this is just to randomly excite it. You saw there was a broad band frequency excitation.
Yeah.
And when we look at the state of the flow, it looks like a turbulent boundary layer. That is why I think that's what we think it's doing. In the turbulent case, when you have a separation bubble, you don't have that possibility. So it'll be interesting to see what it would do in that particular case.
Okay. So that's somehow suggesting also that if you keep the example you just showed nowadays, this seems to me, but correct me if I'm wrong, it seems to suggest that the Pareto curve you showed is actually basically it's a limit of the control, and nonlinear control in that case would simply help to optimize the cost of the control rather than having to control like a large bandwidth. You just control nonlinear effects, but you cannot perform kind of better by reducing the bubble size, but by reducing the cost, right?
I think so.
Okay. That's very interesting, because it seems there is actually a scale of the flow which is much more difficult to suppress, actually.
And also, if you go to three-dimensional flows,
Yeah.
you mentioned this, that's another interesting application, because now pressure, which is really measuring sort of an overall global response, is probably no longer, this is again a hypothesis, probably no longer sufficient. You may have to make measurements of shear stress in this particular case. And that, I think, that's another interesting problem to look at as well.
Yes, because basically, okay, so that's correct. In that case, but in that case, do you expect that the synthetic jet somehow can undergo modulations which may potentially create other sorts of instabilities simply due to the nature of the synthetic jet? You know,
I mean, that's a good question, and there's several colleagues in the field. I know that Professor Mikiyamate at RPI has looked at this quite a bit and published some work on controlled three-dimensional flows using these synthetic jets. So that is certainly a question. On the one hand, you want your actuator to have the bandwidth, to be able to attenuate multiple types of instabilities. But on the other hand, if you don't do things appropriately, you can destabilize. So that's the challenge.
That's correct. Okay, so let's see if there is someone else who would like to ask a question. So just once again, feel free to unmute your mic and ask a question, or you can directly write in the chat.
I might have a question.
Yeah, please go ahead.
So thank you very much for a presentation, Professor. I might have a question, might be silly. Anyway, when you were talking about your reduce all the models, you were presenting a free parameter penalizing near in the past observation over far in the past observation. Am I right? Isn't it?
Correct.
So this is kind of filtering. So you're just taking some kind of frequency in some kind time scales of your observation. So my question is how the amplitude or frequency of your forcing is affecting the time scale of your problem and the receptivity, and whether do you think would be interesting to connect this parameter with the amplitude of the forcing, because keeping this value constant to some uncontrolled estimates might be detrimental for the search of an optimal control function. I hope that being clear helped that the question was clear enough.
Yeah, so you're really talking about that kappa, which is that forgetting factor, right? And on the one hand, if you leave that at one extreme, essentially what happens is it just becomes sort of a running average. And any new data that comes in, it only has a very incremental effect on the results. On the other hand, if you take it to the opposite extreme, where it's only using a very limited number of snapshots, if you will, of data, some prior history, then you tend to have more and more noise to deal with due to the randomness associated with this, both uncertainty in the measurements and just the stochastic nature of the flow. So the good news is that we found that we could vary that kappa over a pretty wide range, and it didn't have much of an effect, at least not that we could see. But we didn't really quantify precisely how sensitive it was to that. And there is the question of how does it actually change the observation? I don't think it changes anything in the dynamics. I think what it does is it changes your ability to detect the dynamics. So it really changes the overall response of the system. How that interplays when you turn on the control is a study in and of itself. And I don't really have the answer for you, Fabio.
Thank you very much for your answer, Professor.
Thank you. So let's see if there are other questions. Once again, just feel free to unmute your mic, or you can write in the chat. I can report the question. This doesn't seem to be the case. I may have a last question if if I can. That's actually I was thinking to the discussion you just had. Basically, as far as I understand this, the role of kappa somehow would affect potentially the cost of the control, because if we have no memory, it means that we need to invest more energy to control it, because basically every control is instantaneous. And if we have too much memory, then fast frequencies are not taken into account, right? It's kind of a trade-off.
Yes, yes, inherently it's a trade-off.
Okay. Thank you. That's was very clear. So thank you once again, Lou, for the very interesting talk, and thanks for having accepted the invitation.
It was my pleasure, Francesco, and maybe sometime in the not too distant future we can do one of these things in person instead.
Yeah, sure. Yes, so, definitely. Thank you again. Have a good day.
All right, thank you, everybody.
Bye.
Bye-bye.